Good day, students. Welcome to the third recording of Module 5, Chemical Changes in Fats and Oils. In this section, we're going to focus on kinetic aspects of lipid oxidation. So as we had already mentioned, that lipid oxidation is one of those problematic chemical reactions that take place in lipids in the food industry because it affects the sensory perception of a food product. So if I was to buy a product from the shop and it has oxidized, I would clearly return it and get my money because it contains compounds that are not desirable. It smells bad. It's off-putting in terms of color. So as a result, oxidation is monitored very carefully. And how we go about doing it in the food industry, we measure certain products or we track certain products that form during lipid oxidation. So the first one is we measure the accumulation of peroxides. We mentioned that peroxides usually break down. So by measuring the accumulation, we make sure that they are at their lowest concentration so that they don't increase and then break down. We measure the rate of oxygen uptake. That can even tell you the type of fatty acids that are contained in a food product, because if the rate is quite fast, then you already know that you have a lot of unsaturated fatty acids. And then important, we also measure the concentration of secondary lipid oxidation products, and we mentioned those are the ones that bring about the bad sensory, the bad attributes of color and then taste. And then another one that's also done is organoleptic evaluation or sensory evaluation. There are people that can actually, that are trained as sensory panelists that can smell the different types of oxidation products. They can tell you this is decanal, this is hexanal, or whatever type of aldehyde or product, because they are so well trained. So it becomes very important to monitor lipid oxidation. So monitoring lipid oxidation, why do we do that? As we mentioned, that lipid oxidation takes place during processing and then manifests itself throughout storage, and then by the time when you buy the product, then you can then taste the off flavors and see off colors. So it means that it then becomes significant in determining the shelf life of food product that contains lipids. So by checking how long does oxidation take, whether it's accelerated oxidation or normal shelf life storage when you are producing a new product, then you can be able to determine how long will this product still be safe and not have lipid oxidation until it's bought by a consumer. And very important in terms of this monitoring of lipid oxidation or lipid oxidation assays, they have to be accurate and sensitive. Accurate in such a way that it must tell us that we are measuring peroxides and there are so much peroxides, because there are some methods whereby at a certain concentration they cannot pick up the analyte, but they have to be very accurate and sensitive in such a way that it can even measure 0.0001%, if you know what I mean. And in terms of lipid oxidation, we mentioned that lipid oxidation is a stepwise process with different products formed in different stages. So you wouldn't just rely on just one test. You won't rely on just your peroxide value. You must also do other things like oxygen uptake, your secondary lipid oxidation products, because you wouldn't know how far in the whole process that reaction would have taken place. So that is why you have to have multiple assays. And then you also need to identify the products. At the end of the day, it's not the matter of saying, yes, it smells bad, yes, it tastes bad, it takes like oxidative rancidity. You should be able to mention that it's because of aldehyde formation, it's because of ketones or this type of aldehyde 6-hexanal or hexenal, whatever type. So it has to identify the specific product, because in terms of lipid oxidation, we know which fatty acids produce which product, and in that way it helps us track the lipid oxidation. And as we already mentioned, part of multiple assays, it has to be multiple assays that actually include both primary and secondary lipid oxidation products, because remember we mentioned as lipid oxidation undergoes stages. So you will want to find out how far in the stage. You don't want to measure your peroxide value and find it at 0 and you're like, yay, no lipid oxidation took place. Meanwhile, actually, those lipid hydroperoxide have decomposed, have moved on to the next step of your secondary lipid oxidation. So there would be no peroxides because they've decomposed, and then you are happy that there's no lipid oxidation. Meanwhile, there is lipid oxidation. So that is why those multiple assays that are then conducted, they must also include both your primary and your secondary assays. Okay, so of the lipid oxidation assays, there is a whole lot of lipid oxidation assays. This is just a few of those. And as I already mentioned, they need to be targeted for both your primary and your secondary lipid oxidation products. So under the primary lipid oxidation products, we have your peroxide value, we have your acid value. We can actually say an acid value is an indirect measure of lipid oxidation, and I'll explain later why. Acid value usually is more a direct product of hydrolysis, when the fatty acids are broken down or are hydrolyzed from the glycerol, so they form free fatty acids. So then if you want to measure those, you measure the acid value. But I had mentioned in the last recording that your free fatty acids affect lipid oxidation, because when the fatty acid is in free fatty acid form and it's no longer esterified to glycerol, it becomes more prone to lipid oxidation. So it's more of an indirect method. I'll still talk about that later when we talk about chemical changes during deep frying. And then we've got the skull oven test, and then we've got what we call the active oxygen method. So that's your primary lipid oxidation assays. When it comes to the secondary, we have your anisidine value, we have your T-bars, that stands for thiobarbituric acid reactive substance. That one should be very familiar. We have what we call the volatile profiles of all the volatile products that are formed. We have the total polar compounds, oxidative stability index, and it's also known as the trademark, the RANSI, MAT, RANSI for rancidity, MAT for, I'm assuming, equipment. We've got what we call thermogravimetric analysis, whereby we measure the weight of the fat after oxidation, because obviously the oxygen would have been bombarded the product. We have what we call differential scanning calorimetry, and then we also have a sensory evaluation with people that are actually trained. So we're not going to discuss all this, but I just chose at least one or two primary and secondary lipid oxidation assays. So the first one, the most commonly measured one, that's why I included it, is the peroxide value. So this is the most widely used concept in lipid chemistry. It actually measures the peroxide concentration of an oil, and then the results thereof are expressed as milliequivalent of peroxide per 100 grams of fat. So the principle in this assays is that it actually measures the amount of iodine, that is usually formed by the reaction of peroxides with the iodine ion. So peroxide that would have formed, we react with iodine, and this is actually a titrimetric kind of assay. Okay, so what happens is that when the peroxide value of the lipid is actually followed, there's usually a curve drawn. If we can just go back to the lipid oxidation mechanism, or the pharma's hydroperoxide mechanism, we had mentioned that in stage 2, the stage 2 is what we call the self-propagating step, whereby your peroxyl radicals are formed and therefore later on hydroperoxides are formed. So that then coincides with this curve that we're talking about, that what happens is that at the first, the PV increases slowly at a uniform rate. However, until it reaches a critical value, there's a sudden drastic increase in rate, and that is obviously due to the fact that there's initiation that must start taking place. There's also the addition of oxygen, but once it gets to the propagation step, then obviously the peroxide production increases at a higher rate. So the first slow phase then of formation of your peroxide is known as the induction period. And as I already mentioned, the autocatalytic nature of this course is obviously explained in the basis of the free radical chain mechanism, whereby I mentioned that in the propagation step, that's when there's then the increase of peroxides. So during the induction period, the initiation occurs, and as we already know, I'm keeping on repeating this, for each free radical which is transformed to a hydroperoxide, there's another free radical produced because of the propagation. So what happens is that during these reactions, as the concentration of this hydroperoxide increases, they increase and accumulate, and then after accumulation, that's when your hydroperoxide decomposes. So meaning, as it increases, it will obviously reach a plateau, and then it will start decreasing. It's decreasing because those lipid hydroperoxide would have then graduated into secondary lipid oxidation products. So these reactions, they generate more free radicals than what's needed for the propagation of the chain reaction at a constant rate. So that is why it is termed, it's autocatalytic. So this diagram here is just showing you, it's a graph showing you the oxygen uptake that is obviously correlated with the peroxide value. As you can see, as the oxidation starts, there is a low concentration of oxygen uptake. Okay, so the rate of oxygen uptake becomes slow because remember, we still need to do what? The first step, initiation, and then when propagation starts, then as propagation starts, there's more and more free radicals produced, there's more and more oxygen required, then it increases, and then it shoots up because then each and every fat in there will definitely be oxidized. So that's a typical curve of the lipid oxidation when it comes to a rate of oxygen uptake. I'm not going to talk about all the other primary assays. I'll just focus on those two. And then the secondary assays, very important. One of the most famous one will be the T-bars. T-bars, as I already mentioned, stands for thiobarbituric acid reactive substances. I'll even mention how this term came about. So when we were doing the practical in a few months ago, in March, in February, we did the TBA test. So what I'm expecting you to do, I'm not going to repeat myself, I'm expecting you to know the steps as they are. So you need to know the steps of what do we react, at what concentration or what moles, for how long do we react it, and what do we do after that. I expect you to know that. But in terms of your TBA or T-bars method, this method actually involves the reaction of your oxidized fat with TBA. TBA is an acid, it's thiobarbituric acid. So what happens is that when TBA then reacts with oxidized fats, it gives a red complex. So this is showing two test tubes whereby there's lipid oxidation. So this is how it looks when there's no oxidation at all. And this one, that's when there's the reactivity of the oxidized fat with the TBA. So after that, red colored complex is actually measured at 532, and this is also a spectrophotometric method. So the TBA test actually correlates well with the degree of rancidity. That's what it's said out there, because the higher the amount of oxidized fat or secondary lipid oxidation products in there, the darker it becomes. And this can also be correlated with the number of double bonds. I mean, remember in the practical we had coconut oil or coconut fat, we had olive oil, we have sunflower oil, we had crude, and the results that we obtained were also correlating with the number of double bonds those lipids contained. So what happens is that there's some discrepancy in terms of this TBA or the T-bars method. What happens is that in terms of the T-bars is specifically for reaction of the malonaldehyde, which is usually formed during oxidation of your linoleic acid and linolenic acid. So that actually means that if that's the case, if we are targeting malonaldehyde or malondialdehyde with the TBA test, it means that if you have an oleic acid which is C18-1, you are not supposed to react it with TBA. You are not supposed to do the T-bars test, because then malonaldehyde is not formed. So it means that there are discrepancies. However, out there in the industry, this is the method they use for almost every food product without checking what are the composition of the lipids in there. And then also another discrepancy that was found was that in terms of the TBA actually, they found out that it's not specific to malonaldehyde. It doesn't react with oxidized fat that contains malonaldehyde only and produce a red color complex. So what happened is that this TBA was reacting with proteins, aldehydes, sugars, nitrites, and nitrites to also produce a red complex. So sometimes it was actually way over estimating lipid oxidation, because some products would still have a red complex color. Meanwhile, there was no oxidation, but that would have been due to the interference of other components that are found in food. And looking at these components here, these are your normal components that almost each and every food product contains. So that is when it was decided that, okay, so for us to minimize the reactivity of TBA with everything else, in terms of a sample, when you want to do the T-bars test, one has to extract the fat. Extraction of the fat, and remember we also did extraction of the fat. You can either use trichloroacetic acid, or you can also use acetic acid vinegar at 20%. In that way, you isolate the fat out and isolate the analyte from the finished product, and in that way you minimize obviously reactivity. So you don't analyze using the actual fish cake or the actual polony or Vienna. You extract the oil from there, and after extracting the oil, then you do the reactivity of TBA and that oil. In that way you minimize interference. Okay, so like any other chapter that you do in food science and technology, we always talk about factors affecting whatever reaction that we're talking about. So the different factors that affect lipid oxidation, there's a whole lot of them. It's affected by the catalysts. The catalyst will be your metals, your light, your heat, and then your enzymes, and especially another one, the free fatty acids. Oxygen affects it. If there's no oxygen, even if the hydrogen is obstructed, there won't be any oxygen to react with the alkyl radical. The type of fatty acid, do we still need to go there? The free fatty acid content in there, the water activity, processing, obviously, because in food science and technology we employ high temperatures, even lower temperatures, that can then affect the stability of the components, and in this case your lipids. And then the antioxidants that are added will then obviously either accelerate or will then reduce, depending on the type of antioxidants. So we already mentioned catalysts. So there is a textbook that I have a link for on Blackboard, which explains all of this factors are affecting lipid oxidation, environmental factors. So go read those textbooks for in-depth understanding. I'm just going to summarize here. The catalyst we already mentioned, lipoxidase becomes a catalyst if it's present. However, we already mentioned since it's an enzyme and a whole lot of food products are not consumed raw, they are processed, especially blanching. So then it becomes inactivated. However, if it's present and the fatty acids are in a 1.4 pentadiene cis, then obviously that the enzyme is going to catalyze the reaction. And then initiation, we already mentioned your heat, your metal, and your light. So if you have to store the product away from light, store it in the refrigerator so that you lower the temperatures that allows oxidation to take place. And then oxygen also affects, because we already know oxygen comes from the atmosphere. Go read about that. Fatty acid type, we already mentioned that in order to minimize lipid oxidation, you definitely have to incorporate your more saturated fats in your product. But there's obviously problems with saturated fats and health and stuff like that. But you need to know that to be able to retard or the rate of reaction, then one has to then use fatty acids that are less prone to oxidation. Go read about that. Free fatty acids. Free fatty acids, I just used this diagram to illustrate free fatty acids. So your fatty acids, like I had mentioned, that free fatty acids are not natural in oil, in raw material like your seed oil, sunflower oil, but they are then broken, hydrolyzed, once those seeds are then stored in humid conditions, and then hydrolysis takes place. So if you can see here, this is how a triglyceride looks like in your fatty acid, in your food product, let's say your oil. So this is a triglyceride, and that is the natural form of your fatty acids. However, due to enzyme and hydrolysis and everything else, high temperature processing, the free fatty acids is then broken, hydrolyzed from the glycerol molecule. You can either end up with monoglyceride or diglyceride, or with glycerol only, depending on whether it was partial or complete hydrolysis. So what happens is that, as we already know, that free fatty acids has both your hydrophilic side and your hydrophobic. So immediately when your free fatty acid is cleaved from the glycerol, the water-loving part, the hydrophilic part, does not want to be associated with the oil. So that's when the free fatty acids then orient themselves to the surface of the oil, because it wants to get away. It wants to go to that air oil interface and not in the oil, because it's highly hydrophilic and the oil is mainly or totally hydrophobic. So by the free fatty acids just moving up here, what it happens is that it lowers the surface tension. It's more like leaving your door open, and then the thieves can come in. So by actually moving to the surface of the oil, it actually reduces the surface tension for oxygen to come in. I usually just make an example in terms of let's say you are at home, it's at night, and you know there are thieves out there, so we lock the door. So locking the door is when all the free fatty acids are esterified to glycerol. But opening the door is when you go open the door and then you expose your head outside. Meanwhile, your whole body is still inside the house. So the thieves can come and then push the door because it's already almost halfway opened. So that's what free fatty acids do. They allow free access of oxygen because they reduce the surface tension for oxygen to enter, to dissolve in there. So that is why they become catalysts. And then water activity. Water activity is another phenomenon that is a bit confusing, but we'll just have to go through it. So looking at the relative reaction rates of different chemical reactions, I think you've done this when you were doing water in food analysis too. So here it talks, you can see lipid oxidation. So lipid oxidation at low water activity is quite high, and then decreases as the water activity increases, kind of plateauing, and then it increases again. The reason for that is that at low water activities of between 0.1 and 0.2, and then high water activities, especially between 0.6 and 1, the rate of reaction is increased. Lipid oxidation rates are increasing. And the reason being, you know, at low water activity, it means there's less water. So the actual oxygen has direct access to the oil. It doesn't have to go via the water. So oxygen will still have to dissolve and go via the water to get to the oil. So when there's no water, it has a direct access there. That is why oxidation is also increased. And also at the same time, at this low water activity, that means that your catalysts, like your iron and your copper, are not hydrated. And when they are dry, in dry state, they function much better than hydration. However, as the water activity increases, there is a decrease in lipid oxidation, because what happens is that at this point you also find that your lipid hydroperoxides then start degrading. However, when there's water at that point, they will form bonds with the water. They will form hydrogen bonding with the water, and then it's not easy for them to actually break down. They become stabilized. But then as the water activity increases again, there's also now an increase in rate of reaction in terms of lipid oxidation, and this phenomenon is attributed to the fact that now, because of water is a medium in which all chemical reaction takes place. So the water serves as a transport for the components to react with each other and moving about. So that is why water activity is a bit confusing, but in the notes it explains it very well, and you need to understand it. Processing, as we already mentioned, in processing, there's a whole lot of processes that we do. We dehydrate, we freeze, we pasteurize, we sterilize, everything. And then we make an example of processing. We talk about ground beef versus steak. So by grinding the meat, you are exposing especially your marbled fat, the fat that was hidden in between where the oxygen could not get to. Once you process it and you ground the beef, then the fat becomes exposed by increasing the surface area. Frying, when you fry, you are exposing to oxygen and high temperatures, and then we know those will then accelerate lipid oxidation. Look at the processing of your palm oil. Look at the equipment that is used. Those equipments are made up of metals. So at those high temperatures, those metals, they shave in there, and then you get that the problem. So that's in refining. And then emulsions also become a problem. Go read about that. So now what we do is that we make sure that the product is safe. We put it in the fridge. Make sure you use the best packaging where oxygen is not going to get in there. There are so many physical ways that you will do, but you can do as much up to a certain point. So one of the other things that we do in the industry chemically and not physically is the addition of antioxidants. Antioxidants, or anti, against oxidation. So antioxidants are substances that are used, especially chemicals added into food, and they retard autooxidation. But when something is called an antioxidant, think about when they say someone is a hero. You might be a hero because you saved somebody from drowning. You can also be a hero because you donated something to someone that needed something or whatever, money or whatsoever. So you saved somebody's lives in so many ways. So an antioxidant, when something is an antioxidant, it doesn't have one function of preventing that oxidation. So a substance may act as an antioxidant in a variety of ways. First of all, it tackles all the problems that are brought up by oxidation. So what antioxidants can do, they can bind oxygen, because we know oxygen is a problem. So you bind it, you hold it, you arrest it. It retards your free radicals. It can inhibit the catalysts. It can stabilize the hydroperoxide. So you can already see that there's a hurdle process of inhibition of oxidation, not just in one form, but in different ways. So all these mechanisms, what they do, they are found in the food system, and they are the most important ones are those that block the propagation step, because the propagation step happens to be a problem. It's the chain reaction. So once you can just prevent the chain reaction, you've actually won the battle with lipid oxidation. So what they do is your antioxidants, they block the propagation And what happens is that an antioxidant, what it usually do is that the antioxidant AH acts as a hydrogen donor. It donates. So if it donates something, it will always donate a hydrogen to what? To the radicals. So if you donate a hydrogen to a radical, this is peroxide radical, you will form a lipid hydroperoxide, which is stable. This is an alkyl radical. It's a fatty acid that is in a radical form. If you donate a hydrogen, it becomes a fatty acid again. So what happens is that when the antioxidant free radical is produced, because remember now, if I have a pen and I give it to you, what happens to me? I don't have a pen. So what happens is that once an antioxidant donates a hydrogen, it becomes a radical itself. But we don't want radical. The one nicest thing about the antioxidant radical that is formed when the antioxidant donates the hydrogen, that one is an inactive radical. It does not then start the chain reaction and want to react with something. It becomes stable even though it's called a radical. And in other instances, the antioxidant may be regenerated if a secondary hydrogen donor is also present. So usually we do that when we use two antioxidants that are working in synergy in food science. Okay, so what the antioxidants do, it means antioxidants action increases the length of the induction period, because in the induction period, let's say its initiation is usually your induction period. So if you take away the metals, you take away the heat, it will take long for this hydrogen to be obstructed. Therefore, you're increasing the shelf life. Okay, so what I did here, I just drew that that pharma hydroperoxide formation mechanism. Doesn't look so good, but yeah. So how do antioxidants prevent lipid oxidation? So this is the whole schematic drawing of the reaction without obviously the termination. It stops where the lipid hydroperoxides are then broken down into carboxyradical and hydroxyl radical. So it's showing that an antioxidant, so what an antioxidant can do is that it can be targeted to the metal. The antioxidant can be targeted toward the free radical by donating a hydrogen. The metals, if you have that antioxidant, it will be what we call a metal chelator. You guys still remember EDTA? You can also have what we call oxygen scavengers, like your ascorbic acid that then reacts with the oxygen, and then the oxygen does not go react with the fatty acid. And then you can also donate a hydrogen there. And then you can also form other antioxidants that will then come and stabilize this lipid hydroperoxide so that they don't break further. So you can already see it was mentioned that it's very important that the antioxidant stops the propagation step. So it's important for the antioxidants to actually work here and there before we actually get to the propagation step. Okay, so here it's showing you the mechanism of radical stabilization. So this is the antioxidant. It donates the hydrogen to the alkyl radical, alkoxy radical, and peroxyl radical. And then these are your stability products. And this is the antioxidant radical that we mentioned that is not active. It's not going to react with anything. It's not going to propagate anything. So of the antioxidants that we have synthetic antioxidants and natural one. Natural is good for clean labeling. Oh yes, we want only natural products in our food. However, it has been found and proven so many times that natural additives are not as good as your synthetic, and they degrade easily, especially when the food product is exposed to those processing conditions. So your synthetic ones like your butylated hydroxyanisole, BHA, BHT, PG. Next time when you're eating knickknacks or any product that contains fat, which I think you guys eat knickknacks more than anything, or when you're cooking at home, when you have your fish oil in quotation marks, just look at the ingredients there. They will say oil and then they say with TBHQ. So it means that oil has been already added with the antioxidant. So these are the different types of antioxidants. You need to know them. And how much are they used? They are regulated They are used at 200 parts per million, which is 200 milligrams per kilogram on the basis of fat. So that's the maximum allowable. You guys did legislation, you should know about this. So the requirements of antioxidants. Antioxidants have to be effective at low concentrations. Remember the no observed level limit, the NOL that you did in product development? Yes, so it has to be at very low concentration, because I mean, if you are going to use a lot of that, then it means you are using too much, and then it can be costly. So it should be effective at very low concentration, and we obviously don't want it to also be a hazard. That's why the lowest concentration should be what it's used. It should be non-toxic, definitely. And usually the toxicity of a chemical increases with the dose, isn't it? So that is why we want it low to make sure that it's not toxic. It must be cost effective, because remember, every cost of every ingredient that's added in the food is then calculated on the price. So what's the use that we have our oils that don't oxidize at all, but the fact that the antioxidant costs so much, you now buying a liter of cooking oil for 100 Rand just because of the antioxidant. It has to be soluble in fat, definitely. And then it must have what we call carryover properties. Carryover properties is that if the oil was added into the antioxidants was added into oil, into cooking oil, when you are using that cooking oil to fry to make your fat cook or to fry your fish, those antioxidants that are there, they should be able to prevent lipid oxidation when they are now in the fish or in the fat cakes. So those are what we call carryover properties. So these are the different types of antioxidants. I will not expect you to know the actual structure, but I would expect you to know the abbreviation and what it stands for. So the primary antioxidants, of the different ones, we've discussed the primary antioxidants. They interfere with the free radical propagation, so therefore they block the reaction. And then they can be used to create a synergy. One of the best known synergy is citric acid, that's been used with almost every other antioxidant. So go read about citric acid and go read about that. So this video will stop here.